Oh, go!
All right, good morning, ladies and gentlemen. Let's go ahead and just jump right into it here. When a net force is exerted on an object, three things happen. The first.
Y'all remember what this mess is?
The first is the mass experiences an acceleration according to Newton's second law.
Newton's second law.
The force is exerted over a time, which changes the momentum of the mass. So a force over time is impulse. Impulse changes momentum.
That's the impulse momentum theorem.
Inertia in motion. Okay. Number three, as the mass moves, work is done and energy changes.
That's a work energy theorem.
There's a lot of stuff going on here, right?
Yep.
Three different things. How much work did gravity do on the falling mass in your T-lab?
A spinning T-lab, remember that?
So look back in your notes.
See, work is force times displacement.
And
force,
it was a 200. So it was a
200 grams.
So 0.2 kilograms times 10.
Well, you got it right there.
Oh, right here, 2 newtons. Look at that. Okay, and times our displacement, our height. If you look back in your notes, you should be able to find that it was 0.73 meters. Okay, when I plug this into my calculator, 2 times 0.73, 2 times 0.73, and we get 1.46.
1.46 joules.
1.46 joules. Okay.
So that's the work that gravity did, pulling down on the mass that made the T spin around.
Okay. And similar ideas here. When a net torque is exerted on an object, three things happen. Okay.
Well, can you guess with what we've seen already?
Well, we talked about Newton's second law. We talked about work and kinetic energy, and then impulse momentum, right?
Yep.
So what do we think our first one is? Okay. This is in a parallel universe, the same idea of Newton's second law, right?
That's Newton's second law right there.
Acceleration. We have the same exact idea as impulse, even though impulse isn't directly in here, but we have a force over a time interval, which equals mass times the angular velocity, which equals the change in momentum.
Change in angular momentum, that's right.
Angular momentum, yes. And then we have rotational work. Just like work was force times displacement, here we've got rotational work is the torque times the angular displacement.
Yep.
Okay, same ideas, the same things happen.
So you got this stuff down, boys and girls.
Okay. A constant retarding torque of 12 newton meters stops a rolling wheel of d equals 0.8 meters in a distance of 15 meters. How much work is done by the torque? So let's see, the work of the rotational was the torque times work is force times displacement, like that, right?
Angular displacement, that's right.
Okay, and we're just trying to figure out this.
So they give us the torque, we need to find what the angular displacement is.
Newton meters.
So the diameter of the wheel is 0.8. What would the radius be?
The whole thing is 0.8. Half it's going to be
0.4.
0.4. Okay.
And the stripe on the ground is 15 meters. What's that equation? Let's see. It's
okay, the stripe is 15 meters. The radius is 0.4 meters. Wasn't it S equals R theta?
Yep. So
Okay.
theta is...
Let's figure out theta. So theta is S over R. My stripe on the ground, it says it goes for a distance of 15 meters, and the radius is 0.4 meters. Okay, 15 divided by 0.4. 37.5.
37.5 radians.
0.5 radians.
So now we've got the angular displacement and we've got the torque, so we can find the work.
12 meters times 37.5 radians, and work equals 12 times that number. So we get 450.
450 Newton meter radians. Now, Newton meter radians, the radians just go away. and Newton meters is a joule.
Okay. So how much work is done by the torque?
450 joules.
Okay. Work changes energy.
Yep.
Yes, it does. Rotational kinematic energy is defined by this equation.
Oh yeah, that's just like the regular kinetic. Translational is 1/2 mv squared. That's 1/2 moment of inertia times the angular velocity squared.
What was the rotational kinetic energy for the spinning T?
Well, we're going to need 1/2 I omega.
We don't need this anymore.
No, we don't. So looking at the data, we calculated the
Yeah, so looking at the, if you guys want to take a look at my worksheet from, so this was the answer key that this is look at this little rock in there. This was the answer key we went over a couple of days ago for the lab, and we figured out the moment of inertia for that mass on the when the T was spinning.
Yep.
Okay.
And what we had to do is we had to find the angular acceleration, which was 0.432 radians per second. You can use that angular acceleration to find the final angular velocity.
We also found the torque.
Yeah, well, we're not going to, we'll ignore that for now.
Yeah, we know that part. Yeah. Okay, so our moment of inertia, we don't have, oh yeah, we have it right here.
Yeah.
Okay, so that's going to equal, oh, look at that. It's all on the board for us. Okay, 1/2 times 0.058 kilogram meters squared.
And we calculated the final angular velocity by taking the original velocity, which was 0 times the acceleration times time. We just multiplied it out times that.
We did this. And we put in our angular acceleration, which we have on that sheet, and our time was like 16 or something.
And you multiply that together and you get 7.1 radians per second. Don't forget to square that.
Oh, this right here.
That's my trick.
Forgetting to square it.
This alien handwriting here.
Okay, so we've got 0.5 times 0.058 times 7.1 squared. And I've got 1.46.
1.46. That number sounds familiar to me.
1.46 joules.
Work changes energy. Woohoo!
Okay,
so we got
work
this.
changes energy.
We got this from the little hangy down thing, the 200-gram mass that was falling.
Yeah.
And then from the data collected, we come up with the kinetic energy. So, the kinetic energy.
So that's it. There it is. Okay. A flywheel. So this is a flywheel energy storage device. And these things are magnets right here. Yeah. So the device is basically like floating.
It doesn't have like regular bearings like ball bearings. The bearings are magnetic, so there's no physical contact between the surroundings and the thing that's spinning. So it has very low friction, And they have a vacuum pump over here that pulls the air out, so there's little air resistance.
Less friction, even air resistance.
Yeah, and so this thing can be spun up by this motor here to very high speeds.
The rotor spins.
Yeah, and as it does that, it has kinetic energy. And then if you want to get the energy back out, the motor turns into a generator and generates electricity. So it's an energy storage device from a flywheel.
And didn't I forgot, you were telling me an example of this.
Well, there was back in the 1950s in Switzerland, they made a bus that had this huge flywheel in it that spun up, and they would use the flywheel to store energy when it was going downhill to help it going uphill.
Oh, and that's right. And you talked about how your like Tesla.
Right.
The batteries, maybe you guys don't know, but when you break a car, sometimes it says it's charging, right?
Yeah.
And that's the idea of it storing that rotational from the rotor, that rotational kinetic energy, and then using it later as
kind of works like an electrical battery, but instead it's storing rotational kinetic energy. Sweet.
Okay, so here we are. I can get rid of this part now, right?
You can. We're done with that.
A flywheel energy storage device, like we just saw, with a moment of inertia of 2 kg/m squared is spinning at 20,000 RPMs. What is the kinetic energy?
Well, K is 1/2 I omega squared. We got the I. How can we get omega out of 20,000 RPM?
Okay, well, I think we did this already. Should I do it on the board with them?
Or you could show them my bad handwriting. It's your call.
I'll do it on the board with them.
All right.
Okay, so I'm just going to go ahead and plug this in real quick right now. 2 kg/m squared. And we need to figure out what's going to be our radius squared right here. What is the number that goes right there? Okay, so we have 20,000 revolutions.
In 1 minute. So on the bottom, you got minutes.
1 minute. And what are we trying to go to?
We want radians per second, so we got to go from minutes to seconds.
So in 1 minute, there's 60 seconds.
And then we want to go from revolutions to radians.
Okay, so in 1 revolution, we go 2 pi radians, right?
Yes, ma'am.
And I think you already plugged that in.
Yeah, it's 2,094 radians per second.
Per second. Oh, revolutions cancel. Radians and seconds don't cancel. There's more seconds. There you go.
There you go.
Okay, so then we just plug that right here. Radians per second.
So how much energy is stored?
0.5 times 2 times 2094 squared. And we get a lot, a big number. Let's see, 4 million, let's put it in a scientific notation. 4 we'll call it 38 times 10 to the 1, 2, 3, 4, 5, 6.
10 to the 6 joules. That's a lot. So, yeah, because the energy increases with the square of the angular velocity. If you spin that thing up, you can store a lot of energy in that thing.
Okay. Can there be rotational potential energy?
What is potential energy?
Well, energy is potential energy is stored. You know, when we move up, when we have more from a certain height.
Gravitational potential energy. You got potential energy stored in a spring. Okay. That's stored, but can there be rotational potential energy?
The answer is no.
No.
There isn't. Okay. So there is not.
Thankfully, and you'll see in a moment why it's a good thing while there's no rotational potential energy.
Yeah, thank goodness. Okay, law of conservation of mechanical energy is that the energy in the beginning equals the energy at the end. You've seen this before?
Simple thing, yeah.
So, when this is why we're happy there's not potential.
So now, before mechanical energy was kinetic and potential.
Yeah, it was just K plus UG, right?
Yeah.
And now we have our total energy is going to be UG, just UG. But we have to think about kinetic energy, translational, up and down. This is how we were thinking about it before.
Yeah.
Plus rotational, if it's
so now we have 3 things.
And nothing. It's the exact same idea.
So now you have a wider base on your pyramid. Now, notice how many of these there are, and why do you want to always start out with this?
Because they cancel, right?
There's some things that are going to be 0 that you don't have to think about. Yeah. So instead of going right to the 1/2 mv squares, the mgh's, the 1/2 whatever, you can just cancel out what you don't need and only use what you do. Put this in your notes, boys and girls.
Do it now. Okay. So I want you guys to go back through Friday's lab, which was the T-lab.
It might not have been on Friday. So whatever, what says Friday?
Oh, we forgot to fix this one.
Yeah.
Anyways.
The spinning T-lab.
Go back to the spinning T-lab, and honestly, we took a break from this, so we just got back to it. It's been like a month. But we did this the other day with you guys. Go back through the lab and step by step to see if you understand everything.
Okay.
All right. That's your homework.